Hey guys, and welcome back to another chemistry lesson. Today we're going to talk stoichiometry. It's our word of the day, stoichiometry. So stoichiometry, first of all, before we jump into it, what is it? Well, it's a section or a branch of chemistry. It's not really its own branch. It's a practice in chemistry anyways. It has to do with relating number of moles, which can also be converted into mass, of reactants and products. So like if I tell you how many grams of a certain reactant you have, you should be able to tell me how many grams of a product I could produce using that. So it's a really handy, probably one of the more practical aspects of chemistry. If you were to work in a chemistry lab or if you were to work in a factory producing chemicals of some sort, stoichiometry is super basic to what you are doing. Let's say you run an aspirin factory and you know which chemical reactants are required to do the reaction that will spit out some aspirin. And so you want, we need to make, 1,000 tons of aspirin this year. How much of each reactant am I going to need to order? So you're going to have to change that mass into moles and then go find your moles of your reactants and then change those moles into mass, and that's how much you can order. So that whole branch of how do we figure one to the other? How do we change grams or moles of one thing in reactants or products into the other side? How do we know the numbers for the entire chemical reaction? That's all stoichiometry. And so this is the reaction we're going to spend most of our time looking at. Let's rewrite it so it looks a little neater. 3 hydrogen gases plus 1 nitrogen gas gives me 2 ammonia. And ammonia is usually a gas, I believe, as well. So there's our starting one there. One way to think about this kind of a chemical reaction is using a sandwich metaphor. Like what is a chemical reaction? Well, it's similar to kind of like a sandwich where I could write, I have 2 breads plus 1 jam plus 1 peanut butter makes 1 sandwich. And it's a ratio of things that have to go together in your recipe, right? So what do the coefficients represent? Well, in my case, they're the ingredients in the sandwich. But if you look at an actual chemical reaction, the coefficients represent individual molecules. So this reaction here says I need 3 H2 molecules to combine with 1 N2 molecule. And that would form 2 NH3 molecules. So the very, very, very basic, smallest possible combination you could get to make this happen is you need 3 hydrogen molecules and 1 nitrogen molecule if you want to make ammonia. It's the same with like if I wanted to make this sandwich, I need, at a bare minimum, 2 breads, 1 jam, 1 peanut butter. That's how I make my sandwich. If I have 12 breads and only 1 jam and 1 peanut butter, I'm still only making 1 sandwich because each sandwich is going to take up that 1 jam and 1 peanut butter. If I have 4 breads, 2 jams, 2 peanut butters, now I have enough of all of it to make 2 sandwiches. So it's kind of the base recipe, and everything has to come in those ratios. And so our base recipe is in molecules. So if we were to draw this out, we can do this with fancy colors here. Let's do a dark blue. So I've got 1 hydrogen, 2 hydrogen, 3 hydrogens. I guess I could label these. So that's an H2. That's an H2. That's an H2. And I need 1 N2. If I put those together, it can form 2 sets of N H3. There we go. So you can see that on the left side, I have 6 hydrogens, and on the right side, I have 6 hydrogens. If I switch over, my left side is 2 nitrogens, my right side is still 2 nitrogens. All I've done is rearrange them. But you can see it's the same as the sandwich, right? I've still got the two breads, the jam, and the peanut butter inside a sandwich. That is what makes the sandwich. It's just I've got the individual components on one side, and I've got the combination rearranged a bit on the other side. It's the same stuff, just rearranged, and it shows you the molecules that are involved. So in this equation, it's saying 3 hydrogen molecules, 1 nitrogen molecule reacts to form 2 ammonia molecules. That's kind of what we just summarized there. But here's the fun thing. This also represents the number of moles that will react with each other. So if you think about it, let's say I had 6.02 times 10 to the 23 atoms, 1 mole, or molecules. I have 6.02 times 10 to the 23 molecules of N2. Well, I would need 3 times 6.02 times 10 to the 23 to make it work. I would need 3 moles. And I'd end up with 2 times 6.02 times 10 to the 23. I'd end up with 2 moles of product. So not only, it actually tells you the number of molecules, but it is also representing the number of moles, which makes things really handy because now, if it is actually number of moles, what I'm really saying is that 3 moles of H2 plus 2 moles of N2 should give 2 moles of NH3. Moles are handy. We can change moles into mass and back and forth, right? We know how molar mass works now. So this is kind of the key that allows us to figure out, if I give you a certain number of grams of hydrogen, you now kind of know the code to unlock how many grams you'd need or make of the other 2. So let's start with just moles, though. How many moles of NH3 would be produced if I made 6 moles of hydrogen, or sorry, if I had 6 moles of hydrogen and 2 moles of N2? So think about our recipe, right? I got 3 hydrogens and 1 nitrogen. That makes 2 ammonias. What if I had 6 hydrogens and 2 ammonias? What if I double both of my product, or both my reactants? If I double both my reactants, what should happen to my products? Well, I should probably double as well. I should end up with 4 moles of ammonia. Right? So we have enough of each molecule to have 2 reactions happening. So if I have 2 reactions happening, 2 sets of H2 and 2 sets of N2, I get 2 sets of 2 moles. I'd end up with 4 moles of ammonia. Now, sometimes it's not always this easy, not always this cut and dried. So this is something you want to circle, square, highlight, and underline. The equation to figure this out is the moles you have. So I was given 6 moles of H2 divided by the moles you need. Well, I need, according to my chemical equation, I need at least 3 of them. And I can set this up so that it's equal to, what was I trying to figure out? I wanted to find how much ammonia. So I don't know how much NH4 I'm going to get. But I know that my equation tells me I should have 2 moles produced. So the moles you have, I have 6 moles, and I don't know how many ammonias, that's what I'm trying to figure out, divided by the moles you need for one reaction. One reaction is 3 moles of hydrogen, gives 2 moles of ammonia. And so I could solve this. Cross multiply and divide. 2 times 6 is 12. 12 divided by 3. 12 divided by 3 gives me 4 moles of NH4. That's supposed to be NH3. Whoops. So used to the ammonium ion from our naming. NH3. There we go. So moles you have over moles you need. That will solve this out for you every time. Let's try it. How many moles of N2 would I need to react exactly with 9 moles of H2? Okay. How much do I have? Let's do have over need. There's my formula. I have 9 moles of H2. I need 3 moles to make a reaction happen. How many moles of N2? I don't know how much N2 I have, but I know how much N2 I need. I need 1 mole of N2 to make a reaction happen. Cross multiply and divide. 1 times 9 is 9. 9 divided by 3. So if I wanted to react 9 moles of H2, I would need exactly 3 moles of N2 to make this reaction work perfectly. Have nothing left over. how many moles of H2 and how many moles of N2 would be required if I want to make 0.4 moles of ammonia. All right, so again, what do I have? What do I need? I have 0.4 ammonia. And what do I need? Well, the chemical equation tells me I would need 2 of them if I wanted to make, I'm going to do this, I'll do it in 2 separate steps. What do I want to do first, hydrogen or nitrogen? Doesn't make a difference, same steps either way. Let's start with the hydrogen just because it's in front. So I would need 3 H2s to do a regular equation. How much H2 am I going to make? So you grab your handy dandy calculator, because this is probably one you're not doing in your head. You're going to cross multiply and divide. 3 times 0.4 divided by 2. You probably could have done that in your head, actually. And turns out you need 0.6 moles of H2. So that's one of them. Am I done? No, I still need to find N2. So I use the same setup. I have 0.4 moles of NH3, and I know I need 2 of them. I don't know how much N2 I'm going to make, but I know that in my equation, it requires 1 to have a reaction happen. So I do 1 times 0.4 divided by 2, and I need 0.2 moles of N2 gas. So this entire reaction, if I wanted 0.4 moles of ammonia when I'm done, I would combine 0.6 moles of hydrogen and 0.2 moles of nitrogen, and it should spit out 0.4 moles of ammonia. So if I know what I need, I can now calculate how many of my reactants are required to create that much. It's kind of the power of stoichiometry and why it's so handy in chemistry. How many grams of ammonia are produced if I take 12 grams of H2 and unlimited N2? Okay, unlimited N2 is good news. It means I don't have to worry about N2 at all. The number of moles of N2 are unimportant. It's like if I say I have unlimited peanut butter, I can make as many sandwiches as I want until I run out of bread, right? And so in this case, H2 is my bread. This is what I'm going to run out of because I've got unlimited ammonia. So step 1, if I got 12 grams of hydrogen gas, well, grams don't do me any good. We're doing chemistry. I need to find out how many moles I have. So I've got 12 grams. I need to change out of grams into moles. To do that, I use molar mass. 1 mole of hydrogen gas is 2.016. Hydrogen, an atom, is 1, if you look at the periodic table. But this isn't hydrogen, the atom, it's H2. It's 2 of them together, so you just double it. So 12 times 1 divided by 2.016. So I have 5.95, on and on for a bit, moles of hydrogen gas. All right. Now I need to figure out how much ammonia I'm going to have. So what's that formula again? Oh yeah, what do I have over what do I need? Well, I have 5.95 H2s. I need 3 of them to make a reaction happen. I don't know how much ammonia I've got, but I know that when an equation's done, it's supposed to spit out, each recipe should spit out 2 of them. So I take that, cross multiply and divide, and I get 3.968 moles of NH3. So I'm leaving all these decimal spots in my calculator. I'm not getting rid of them. It's not going to round until the very end. Then I round to 2 decimals. All right, so cool. I've got the number of moles of ammonia. Is that what I wanted? Recheck the question. Oh, I needed grams. All right. So I've got 3.968 grams of ammonia. No, I don't. I have moles of ammonia. Whoops. Moles of ammonia. I need to get out of moles and into grams. So I would need the molar mass of ammonia, which luckily has been given to you. Otherwise, you could just calculate it, right? Look it up in your periodic table. I've got 1 nitrogen plus 3 hydrogens. That's what 3 hydrogens is, 3 times 1.08. So I know that 17.03 grams is 1 mole. So take my number of moles times 17.03. And it turns out that I would have 67 point, I'll round to 2 decimals here, 58 grams of ammonia. There's the final answer. So if I have 12 grams of hydrogen, I make almost 68 grams of ammonia. So why on earth is it so heavy? If I'm only taking 12 grams of hydrogen, why am I getting so much ammonia? Well, it's because the hydrogen is so light, like it's so small. 12 grams of H2 is almost 6 moles. So I got 6 moles of H2. That's actually a lot of atoms of H2. And so when they start combining with the nitrogen, which is much heavier, your mass goes way up. So it seems kind of counterintuitive sometimes when you think about like 12 grams of hydrogen and you say, well, the mole ratio is 3 to 2. Like they're pretty close. It shouldn't be that different from 12. And your answer turns up to be like 5 times heavier. It's a little weird, but it has to do with the fact that hydrogen is so darn light compared to what an ammonia weighs. So that answer does actually make sense if you think about the weight of an ammonia being 17 versus the weight of a hydrogen only being 2. And so what we know so far is that we can calculate the number of moles of reactants and products. And if we can do that, we can also do it with mass. You just use molar mass to convert back and forth. So make sure you go to moles first, do everything you need to do with moles. And if you want mass, you change the moles back into mass afterwards. So generally speaking, if you're given mass, you change it into moles. Then you use what we call the mole ratio. That's the what you have over what you need. So you use the mole ratio to convert into whatever else you need to do. So this is mass of reactants. Gives you moles of reactants. You use the mole ratio to give you moles of product. And if you need mass, you use molar mass to give you mass of product. And this goes both ways. You can hop into this equation anywhere. Like if you're given moles already, fantastic. You just kind of skip the mass step and life is good. So that's kind of our general rule of how we do things. If you're given masses, you switch them to moles. You use your mole ratio to convert from one chemical or one element or one molecule to another. And then you're back in the other moles, use molar mass to go to mass. So that's what we've done so far. There's one last part we can include. We can include energy or heat in the balanced equation and use stoichiometry to figure out how much heat's going to be given off or absorbed. So if something soaks up energy or gives it off, we can include that as part of our balanced reaction and use stoichiometry to calculate exactly how much heat will be given off or absorbed. So for example, magnesium reacting with hydrochloric acid. So if you put metal in acid, it fizzes a whole bunch. So I got a magnesium solid and 2 hydrochloric acid. So here's our balanced equation. Gives you magnesium chloride plus hydrogen gas plus heat. There's our new part. We've added heat. Now, if heat is on the product side, it's exothermic. I am producing heat. I am giving off energy. If heat ends up over here on the reactant side, then we say it's endothermic. It uses up heat. It soaks it up. It absorbs it. So if heat was on the reactant side, we'd say it's endothermic. But in this case, it's on the product side. So this is endothermic. It creates heat. It gives it off. And you could feel that. If you touch this beaker, it is getting warm during the reaction. So again, this is exothermic. Heat is being released out into the atmosphere. It is created as a product. And if you were to measure this and actually stick a thermometer in and find out how much heat's being given off, it turns out there's 470,000 joules for each mole of magnesium. That's a buttload of energy. That means that a single mole of magnesium, if you put this into acid, would raise the temperature of a full liter of water by 110 degrees. That's enough to boil it. So if you put a mole of magnesium into acid, you'd end up boiling probably that acid because the acid's aqueous, it's in water, and so that you'd get that water boiling. And so you'd have boiling hydrochloric acid, which is not going to be a good time for anyone involved. So let's just look at this with some math now. Hydrogen gas reacts with oxygen gas. Cool. It just burns. 2 hydrogens plus an oxygen gives you 2 waters plus some heat. If I have 7.60 grams of hydrogen and I react this with however much oxygen I need, and I know how much energy it releases per mole of hydrogen, how much energy comes out? Okay, well, I know my energy is measured per mole of hydrogen, so I'm probably going to need moles of hydrogen. And right now, all I know are grams of hydrogen. I need to get rid of grams. I need to go into moles. Oh, and it's not hydrogen in the atom. It is hydrogen gas. Okay, so what is the molar mass of hydrogen again? Well, 1.08 times 2.016 per mole. There we go. So grab the handy dandy calculator, 7.60 times 1 divided by 2.016. Turns out I have 3.769841 moles of H2. All right. So I've got 3.7698, whatever it is, moles of H2. And that's not what I want. I want energy. What total energy is released? I need to change out of moles of H2 and into energy, which is measured in joules. So what's my conversion factor for joules to moles? Well, it should be given to you in the question. 286,000 joules gives me 1 mole of H2. It's 286,000 joules per mole. So you just take that number of moles, times it by 286,000, and it turns out, wow, it's a big number. 1.08 times 10. 1, 2, 3, 4, 5, 6. So over 1 million joules of energy will be given off if you were to burn 7 grams of hydrogen. Now again, 7 grams doesn't sound like a lot, but it's hydrogen. That's almost 4 moles. That's a lot of atoms. So when those react, they give off a lot of heat. That's why hydrogen gas is so explosive. One more example here. Ammonium nitrate reacts with water. So this is going to be endothermic. We're going to know heat is absorbed. So I'll put heat on my left side here. My reaction is ammonium nitrate. Ammonium nitrate. This is a +1, this is a -1, so that's already balanced. Plus water are mixed in a double displacement reaction. So when you have to do a double displacement with water, treat it like hydrogen hydroxide. It makes it way easier to see the double displacement happen. The NH4 and the H change spots. So I end up with HNO3 plus NH4OH. Luckily, H is a +1 and O is a -1, so everything's already balanced. It's all 1-to-1 to 1-to-1 ratios, which is really nice. Okay, what do I know? This is going to, they are mixed, they absorb 800 kilojoules. So I know I've got 800,000 joules absorbed. If the heat of reaction is 320 kilojoules per mole of ammonium nitrate, so every mole of this should give me 320 kilojoules. How many moles were present? Well, I can use the same formula I had before, way back. Have over need. I'm going to do it in blue so it stands out a little because I'm starting to run out of room. So what do I have? I have 800 kilojoules of energy. And I know that my reaction should create 320 kilojoules for every 1 mole of ammonium nitrate. And I want to know how many moles of ammonium nitrate I have. So what I have is on the top. I know I have 800 kilojoules. I don't know how much of this I have. Versus on the bottom, what I need. And I know that this equation is 1 mole of this gives me 320 kilojoules. So I just pull out the old calculator and do a cross multiply and divide. You take the 800 kilojoules divided by 320 kilojoules, and you're left with exactly 2.5 moles of NH4NO3. There you go. Oh, I could probably add that if these are mixed in water, they are probably aqueous now. And I don't know, NH4NO3 could have been solid, could have been liquid, could have been gas. No, it's probably a solid being dissolved in water. I'm just guessing. Doesn't make a big difference. So I'm not going to tell you in the question. I'm not going to dock marks on it. But that would be my guess. But that's it. That's how many moles of ammonium nitrate we've got here. Yoink. And so this is what a lot of chemistry boils down to, is being able to do stoichiometry to see how much you're going to have, how much you're going to need, how much energy is going to be created or absorbed or given off. And so it's a very important calculation to wrap your head around. So make sure we get lots of practice figuring this one out. Thanks for watching, guys. I'll catch you next time.